So I'd like to ask Stephanie Granger to come up for our next presentation. She's a technical staff and program area manager for NASA Jet Propulsion Laboratory through California Institute of Technology, and she has a number of years' experiences in earth science remote sensing technologies, and she's going to be talking about that remote sensing to help manage water during dry times. Stephanie, thank you for coming.
Thank you, Jeff. I appreciate it. Thank you for that introduction. Can everybody hear me? Hopefully now. Well, first of all, thank you so much for having me. It's a pleasure to be here today. I'd like to especially thank Janine Jones and Jeff for hosting this workshop, and Gina and Brandy for their great organizing. It's been terrific. Forgive me a little bit. I'm getting over a cold, so please let me know if I'm inaudible in the back. So I've been asked to talk about remote sensing products to help manage water during dry times. And I created this little image of a very dry Earth with a lot of satellites going around it. So this is going to be quite a bit different than the talk that you just heard. So I'm going to give today just sort of a high-level introduction of NASA Earth Science remote sensing writ large. Then I'll talk about what pieces of the hydrology puzzle we can and do observe from space as well as from airborne platforms. And you may have heard a little bit about some of that today already. And then I'm going to describe for you some current NASA applied science funded projects that are focused on drought challenges in California. And I'll be actually sort of giving an overview of a lot of other people's work. And so there may be some questions that I would defer to those folks. And if I can't answer them, then I'll give you contact information at the end. And then we're going to take a brief foray into a couple of projects that have promise for the future. One is focused on measurements of snow, airborne measurements of snow in the Sierra Nevada. It was flown last year. And the other is a research project that has potential for improved understanding of groundwater. So first, NASA remote sensing. So when most people think of NASA, they think of manned spaceflight, or they think of the International Space Station, or missions to Mars, unmanned missions to Mars. But what they don't realize is that NASA has many satellite and airborne missions focused on Earth science. And there are also research activities associated with Earth science as well. In fact, right now we're operating 16 satellites that are focused on Earth science. Not all of them are water, but a good chunk of them are water related. Some of them are more focused on atmospheric science or tectonics research. Besides the satellites, NASA also has sensors, has airborne sensors that can provide targeted observations at much higher resolution, perhaps for process studies. So as I said, not all of the satellites and all of the sensors are appropriate for water resources. However, there are several that are appropriate for water resources. And in fact, NASA is keen on applying those science data and research results to challenges that will benefit society. But then we are challenged at NASA in how we advance these data and scientific results beyond the fundamental research and then apply them to real-world problems. And so NASA has an applied science program that they've established, and there are different topical areas. And one of those topical areas is water resources. So first I'll poke at some NASA satellite products that are relevant to drought. This is going to be kind of a high-level poke, really. So precipitation, soil moisture, and snow cover are all measured by NASA satellites in some way, shape, or form. As we all know, precipitation is critical to capture the onset of drought. And although there are several satellite sensors that can measure precipitation. On the precipitation side, I've listed here 2 missions whose purpose is solely to measure precipitation. The first, down at the bottom, you can see this alphabet soup down here, and I was actually going to put an alphabet soup can next to it, but I refrained. The sensor is called TRIM, which stands for the Tropical Rainfall Monitoring Mission. And the other sensor, and as I said, there are many sensors that can measure rainfall, but these are strictly focused on rainfall. The other sensor is the Global Precipitation Monitoring Mission. And the GPM, that's called GPM for short, and that will launch in 2014. These satellites provide daily products, can provide derived daily products. In fact, there are a multitude of derived daily products from TRIM. Some are better than others. And they've been very useful in, some people have taken some of these TRIM products and they've combined them with data from other satellites as well to even produce higher level satellite products. The spatial resolution for TRIM is between 4 and 25 kilometers, which might be a little bit coarse for water managers in California. But the benefit of all of satellite measurements is even though the spatial resolution may be somewhat coarse, the satellite observations provide homogeneous quality of measurements over a broad region. And so they can be complementary to the high resolution, high accuracy stream gauges and precipitation gauges that are located throughout the state and certainly throughout the United States. I'm working on a project that's focused in Africa right now, and we're taking some of these precipitation products and using those as initial conditions into a model. And we're challenged in Africa because obviously there's no ground data. And so the satellite products hold great promise to improve hydrological forecasting in the developing country where we don't have ground data. But that's also one of the difficulties because we can't calibrate what we're looking at. Another important parameter for drought that is measured by NASA is soil moisture. Again, fairly coarse right now, 25 to 40 kilometers, but it is a global product. These are available every 1 to 3 days. I have, again, another alphabet soup of sensors down at the bottom. AMSR-E sensor just recently died, but WinSat is a Department of Defense sensor that is very similar it provides very similar measurement to the AMSR-E, and so the measurement continues, even though the satellite sensor, the AMSR-E satellite sensor, is no longer operational. In the future, we'll be launching I should say that SMOS is a European soil moisture project that is currently providing data. The Soil Moisture Active Passive Mission, the SMAP with the star next to it, is kind of a funny name. And that's another satellite that's going to launch in 2014. And this one we're really excited about. It's actually going to be providing soil moisture every 1 to 3 days at 9-kilometer spatial resolution, which is a huge advancement in terms of satellite remote sensing from what we have right now. One of the amazing things about the SMAP measurement, I should say that the soil moisture is at 5 centimeters. It's not, the entire profile. Yeah, so it's the top 5 centimeters. So the SMAP team has been working really hard to define and develop applications for the SMAP project before it launches. It's one of the first times that NASA has ever reached out to potential users of the data, aside from research scientists, to kind of test out, shake out what we've already got, and to see if, and to provide input on the data formats, timeliness of the data, so on and so forth. It's a good, I think one of the benefits of the SMAP data is for assimilation into surface hydrology models. Snow cover. Right now, MODIS, AMSR-E, and other instruments provide fractional snow-covered area, about 250 to 500 meter spatial resolution. This is not grain size or snow water equivalent, it is just snow-covered area, but it is shown to be useful to, say for instance, I was talking to someone from LADWP a couple of years ago, and they they had no idea where the snow was, and so just a snapshot of where the snow is turned out to be very useful to them. This is my last slide on products. So 3 others. One is vegetation. This is just a simple greenness indicator. I think everybody's aware of this. I'm thinking of the Normalized Vegetation Index. NDVI from Landsat and from MODIS is used quite often in drought projects. And I'm going to sort of dive into a current drought project that is using NDVI from the MODIS, which is the Moderate Resolution Infrared Spectrometer, and Landsat to identify fallowed regions in California. MODIS and Landsat together provide a really great product, a good greenness product at relatively high resolution. Evapotranspiration, we don't measure evapotranspiration directly from satellites. There is a MODIS evapotranspiration product, and there's a group at JPL who have developed an ET product at 1 kilometer spatial resolution, a global product, from many different satellites. It's called the PT-JPL product. PT stands for Penman-Monteith. We were working right now with the Colorado River Forecast Center. They're very interested in the ET product. They're concerned about consumptive use. And so we're exploring ways that we can apply this particular ET product as a direct measure of consumptive use in Colorado, in the Colorado Basin. Lastly is groundwater, and the image that I'm showing there is an image from the gravity I should know what that is. Is from the Gravity Recovery and Climate Experiment, also called GRACE. And GRACE is kind of an interesting instrument. It actually has 2 satellites that infer changes in the Earth's gravity related to water. So the instruments move at different speeds depending upon the gravitational pull of the Earth. And so it essentially weighs all of the water on the Earth. And by removing soil moisture, snow cover, soil moisture, snow cover, and surface water, we can infer groundwater from GRACE. The inhibiting factor with GRACE is that it's very coarse spatial resolution. It's about 100 kilometers, so 1 pixel gives you the entire Central Valley. But we're looking at different ways to perhaps develop a fused product with GRACE and some other techniques that I'll describe later, including what's called INSAR. So I'm going to give an overview of just a few of applied science projects, drought projects, and 2 of these projects, Janine Jones is actually a partner or a co-investigator on, and so if there are any questions, I would certainly defer to Janine. The first one is a project led by Tom Painter, JPL, in partnership with a few folks at the National Weather Service Colorado River Forecast Center. The River Forecast Center is starting to see the frequency of drought increasing in the Colorado River Basin, and so they were really interested in having a more comprehensive knowledge of snow cover to develop more precise runoff forecasting and decision support. So Tom with his team has developed a high-precision snow-covered area product derived from the MODIS instrument, which I just mentioned. And the aim of his team is to integrate these products with the operations of the Colorado Basin River Forecast Center to improve decision-making under drought conditions. This project just completed their 1-year feasibility stage, and they've ingested some of these products, and I've got some visualizations up and running. And in this slide, we show the results of the evaluation of the assimilation of the snow products with the modeled runoff. And on the, it's kind of hard to see, and I apologize for this, but in the, on your right, the purple line shows the adjusted runoff using the improved snow-covered area. The second project is a project called Fallowed Area Mapping for Drought Impacts Reporting and Decision Making. This is led by Jim Verdon of USGS in partnership with USDA, NASA, Ames, and Janine Jones of California Department of Water Resources. And the idea here is to apply remote sensing to assess drought impacts on land fallowing in California by identifying extent or change from historical condition of fallowed area due to water shortages. Mapping of the fallowed areas during drought, this has been identified as a research priority for NIDIS, the National Integrated Drought Information System, by California Department of Water Resources. The eventual output will be a product that will be similar to the NASS cropland data, but it'll be provided on a monthly basis. And here, what I'm showing, this is Landsat, and I believe that the red in this case is healthy vegetation. On the left is 2007, and on the right is 2009. This is one of the input products into development of the fallowed land mapping. Here, this is the NASS, the current NASS fallowed land mapping for the same period, 2007 and 2009. And then here are the results, some results at the end of the first year from Jim's team. So the team applied a decision tree algorithm to time series of vegetation index data from the satellite data, both MODIS and Landsat, to classify fallowed land and achieve this result in the Central Valley. This is from June of 2013. Jim has found generally good agreement between the satellite and the USDA drought, the USDA data, though there are differences, and so the team is exploring what those differences are in the coming year. The coming 3 years. The third project that's relevant to drought, it is funded by the Applied Science Program, is a project that is led by Forrest Melton and his team from NASA Ames in collaboration with DWR, USGS, USDA, and agricultural partners. His aim is to improve estimates of crop-specific ET using remote sensing to optimize irrigation in California. The goal of the project is to develop near real-time estimates of crop water requirements from the satellite data to assist growers in optimizing irrigation and water managers in improving estimates of agricultural water requirements by deriving crop coefficients from satellite estimates and combining these with ET from the CMS system. This project actually grew out of a project that was initially funded by stimulus funding, focused primarily on Mondavi vineyards. So we were Forrest and his team was initially looking at grapes, but he's expanded since then to other crop types. He's now producing data statewide at 2-kilometer resolution, and this is an example of some of the data that are being ingested into the system. And then this is just a view of the system, kind of a Google Earth view. So these data are delivered via either the mapping system shown here, or I think one of the really great aspects of this is he delivers the data on a daily basis to farmers via their mobile phones. And so for my project in Africa, we're actually going to be doing that same thing as delivering information to farmers via the cell phones. And now I'm going to provide an overview of a promising product for estimating groundwater, which I mentioned at the beginning, and an exciting project that measures snow from airplanes. So first of all, this is kind of a psychedelic picture. This is called an interferogram. This is from a radar instrument that's flown by the Japanese Space Agency. And what this is basically a before and after snapshot. So the satellite goes over an area, so one day, and then a couple of days or even a year later, the satellite will go over that same location with the precise geolocation. And the satellite is measuring, or can measure, differences in height of the surface of the Earth on the scale of centimeters. And this map is a difference between the first overpass and the second overpass. And the fringes are areas where the ground surface has changed height. This technique was originally developed for tectonics research. But there were some earthquake guys who were looking at Bakersfield a few years ago, and they'd seen some evidence of movement in the earth. But there hadn't been any earthquakes, and so they were trying to figure out what exactly it was that they were looking at. And somebody figured out finally, they thought perhaps it was noise in the data or there was a problem in their processing, in their code, and they figured out later that what they were seeing was the oil wells in Bakersfield. They were seeing the oil being pumped out of the oil wells, and actually the ground was subsiding as the oil was being pumped out. So then somebody had the bright idea to apply this technique to groundwater. And there was an initial project that was done looking at the Los Angeles basin, and there was a nice time series that was done that shows subsidence and actually shows the land sort of breathing. And the group related the up and down of the land, the up and down movement, to aquifer recharge and discharge. There was a group who worked with Arizona Department of Water Resources through NASA and to do the same thing. And actually, Arizona Department of Water Resources has adopted this technique, and so now they're actively pulling in the radar data to monitor ground subsidence in Arizona, and they have somebody who's actually running the processing code on his own to do that. Here in California, we were asked, again, this was a little project through stimulus, we were actually asked to, just as kind of a research to see what we could do, to see if we could do this in the Central Valley. And so hopefully this works. I don't know if it will. Arg. Of course not. Well, I had a lovely animation, which I can show you offline if you'd like to see it. But this is the Central Valley in California, and we have a time series that goes from 2007 to 2011. And we've processed the data for this period, and it's a little bit challenging, and developed a very nice animation that shows subsidence that we've then correlated to well measurements. It's a little bit of a challenge to apply this technique in the Central Valley because of the fact that we need a before and after picture, and we need the before and after picture to be the same. And so in regions like a desert or a city like LA, there's not much change, but in the Central Valley, there's plowing. So there have been some issues with decorrelation. So the team has worked on some methods to identify static points so that they can reduce the decorrelation, and they've actually brought in a lot more data to actually mitigate some of the decorrelation as well, and they're getting some really nice results. And it's a terrific animation, and I'd love to show it to you offline if you're interested in seeing it. Lastly, Tom Painter of JPL has been working with Frank Gerke at Department of Water Resources and Bruce McGurk, and they've developed and flown the Airborne Snow Observatory that provides high-resolution observations of snow water equivalent. Last year, the team flew the observatory over Tuolumne River Basin, and the results are promising. In fact, I was up in Mammoth a few times last year, and the Twin Otter was parked at Mammoth Airport, and I was, why can't I be on that project? It was like great fun. And this is a picture from the Twin Otter. I'm not sure if they're over the Tuolumne here, but they were flying over the Tuolumne Basin. And in this slide, the team here used the data to improve the inflow projections into the Hetch Hetchy Reservoir. And the purple shows the prediction with the Airborne Snow Observatory data and shows improvement of factor 2 estimates of the actual inflow. And in fact, these data were actually used last year to optimize watershed operations. This is very much a research project. But they do plan to continue flying, and they will be flying, I believe, this year again in California. I'm not sure of the watersheds where they're going to be flying, but I know that there have also been some plans to fly in Colorado as well, fly the Uncompahgre Basin in Colorado. So in summary, I understand that was a lot of stuff, but I just wanted to convey that NASA is actively developing projects to broaden the use and the utility of earth science data. And I just focused on NASA Earth science data. There's a lot of other Earth science data out there from satellites. Satellite remote sensing can be limited by coarse spatial resolution, but can provide homogeneous information over broad regions. It's especially useful in the developing world. Can be used for regional monitoring, especially if we use models as to provide initial conditions to models or to assimilate into models. Airborne is also useful for regional monitoring, especially, say, for instance, process studies. There are different levels of maturity for water resource management. I mean, some of what we've seen today, and we kind of flew through it, is at the point where it's relatively mature, whereas some of these other potential products have promise but are not yet demonstrated. And with that, I thank you. I want to recognize everybody who's provided contributions. And I can. How accurate is the snow water equivalent measurement? So what we observe is snow-covered area. There's a project that is undertaken at University of Colorado at Boulder that actually Mike was a part of advising that project, that's used a melt model to estimate snow water equivalent going back in time. So that's a hindcast. He's now working on going forward in time, but you're right, it is a challenge. The Airborne Snow Observatory uses an instrument called a hyperspectral instrument to get information about the snow itself. But what they do is they fly before the snow is on the ground. They have a high resolution LiDAR. So they've mapped the topography, and then after there's snow on the ground, then they use the same LiDAR to map the height of the snow, and they use the hyperspectral instrument to understand the characteristics of the snow. And from there, they're getting snow water equivalent. Sure.
What kind of orbits are you using for satellites? Are these polar orbits or equatorial orbits?
Yeah. So what kind of orbits are we using for the satellites? Are they polar orbits or equatorial orbits? Both. So the TRIM, the rainfall, the precipitation satellite, is in an equatorial orbit because it's mostly concerned with tropical rainfall. The other satellites are typically in a polar orbit.
What kind of altitude?
These are, I believe they're LEO, low Earth orbit. And all I know is I don't know the number attached to LEO. Dude.
Sure. Okay.
Thank you. Yeah. You mentioned in this talk about providing data to farmers through cell phones and other things, and that kind of technical data. Two companies which are good at doing so are those weather decision technologies, and there is the enterprise AccuWeather solutions. And I was wondering whether you folks are thinking about taking your data and working with them to make some meaningful impact, because what I understood from many of the comments you made, that you did something, why? Because there was money from stimulus or something. But one has to go beyond it. And I was just wondering whether there is any plan to get those kind of companies engaged.
Right. Well, that's an excellent point. So there were two of the projects that I described were seeded by stimulus funding, but the majority of the projects are longer-term projects, of funding from various sources. But in terms of the mobile application, right now, the mobile application that is being used, I believe it's been developed by Ames, NASA Ames. And so I don't know that they're necessarily talking to a commercial provider at this point, although that's an excellent point. Mobile application that we're developing in Africa, we're in some discussions with commercial providers there to do that. But I agree, your point is a good one, well taken, because we need to continue these measurements beyond the lifetime of a particular project.
Thank you.
Stephanie, thanks so much for being here. We do
Thank you.
appreciate it.